Today we're going to talk about the ideal and combined gas laws. Okay, so as a review, in the previous videos you have seen Boyle's law, which gives the relationship between pressure and volume. They are inversely proportional. As the pressure goes up, the volume goes down, and vice versa. And Boyle's law holds true when temperature is constant. Charles' law says that volume and temperature are proportional. This means that as the volume goes up, the temperature also goes up. And Charles' law holds true while pressure is constant. Gay-Lussac gave us the relationship between pressure and temperature, and that is, again, a proportional relationship where when pressure goes up, temperature goes up. And Gay-Lussac's law holds true when volume is constant. So here you have a picture of a balloon being put in very, very cold liquid nitrogen. So at room temperature, the balloons are quite large, but when the temperature drops, the volume also drops. Okay, so for each of the previous gas laws, one of these three variables, either temperature, pressure, or volume, has to be held constant. And constant means not changing. Additionally, for each of these first three gas laws, we have also been holding the number of moles, or N, constant, which is another way of saying that the amount of gas in our system is not changing. Okay. But what if nothing is constant? What if volume, pressure, and temperature are all changing at the same time? How do we mathematically account for that? Well, this is called the combined gas law. And the combined gas law says that pressure divided by temperature times volume is a constant. Or, most often written as P1 V1 over T1 equals P2 V2 over T2. You can cross multiply and end up with P1 V1 T2 equals P2 V2 T1. And this is the combined gas law, when all three variables are changing at the same time. So here's a practice problem. We have a sample of gas at 200 liters, a temperature of 290 degrees Kelvin, and a pressure of 224 millimeters of mercury. What volume will the gas occupy at standard temperature and pressure? So the first thing we're going to do is we're going to identify our variables. So in this problem, our first volume is right here, and it's 200 liters. Our pressure is 224 millimeters of mercury, and our first temperature is 293 K. Our new volume is question mark. We don't know what it is. That's what we're trying to solve for. Our new pressure, since we're at STP, that's 1 atmosphere, or 760 mmHg. And since we're at standard temperature and pressure, the new temperature is 273 K. So now I have to find my variables. So now I'm going to rearrange my formula to solve for V2. So I am going to multiply both sides of the equation by G2 over V2. And what I'm left with is this equation here. Okay? Now all I need to do is plug in the variables that I've already defined and solve. Okay, so P2 equals P1, 224 millimeters of mercury, times V1, 200 liters, times T2, 273 K, all over P2, which is 760 mmHg, times T1 is 293 K. If I cancel my units, I end up with volume in liters, which makes lots of sense, and answer is 54.9 liters. Easy, yeah? Okay, moving on. So these gas laws, Boyle's law, Charles' law, Gay-Lussac, the combined gas law, you have to measure your variables twice. They always have an initial pressure and a final pressure, or initial volume and a final volume. Well, what if you only want to measure things once? The other problem with these gas laws is that we were assuming that in all cases the amount of gas in our system was not changing, that we had a fixed number of moles. Well, it turns out if we only want to measure once, and if we want to use moles, we can use this gas law called the ideal gas law. So you may dream of your ideal girlfriend or your ideal boyfriend or even your ideal dog, but chemists are such nerds that we dream about ideal gases. And ideal gases are things where the space between the molecules is much more important than the size of the molecules themselves. And they're things where the molecules do not interact with one another. The reality is that most gases are not ideal, just like your boyfriend or girlfriend is not ideal. But gases are close enough that we can use this equation. Okay? And in this equation, pressure is P, and it's always in atmospheres. V is the volume, and it must be in liters. N is the number of moles, and guess what? Moles is in moles. V is volume in liters, R is the universal gas constant. Constant means not changing. And that is equal to 0.0821 liters, atmospheres, divided by moles times kelvins. And then the temperature in kelvins. And like the other gas laws, it's really important that you solve these equations always converting T to kelvins. So, here's our practice problem. I have an average lung capacity of 3.9 liters. What do you think 3.9 liters is? Well, I know that liters is volume. And a normal body temperature at 37 degrees C, and I'm going to add 273 to that, and get 310. 273 plus 37. Yes, 310 Kelvin. Okay, my pressure is 1.09 atm. My N is question mark, and R is always 0.0821 liters, atmospheres over moles times Kelvin. So, PV equals nRT. We need to solve for N. How do you do that? Well, what's next to N? The R and the T, and they're multiplying. So to get rid of it, I have to divide. And I end up with PV over RT equals N. Now I can plug in my variables, and I get 1.09 atmospheres times 3.9 liters over 0.0821 liters, atmospheres, moles, Kelvin, times 310 Kelvin. Once again, I'm going to cancel my units, and I end up with moles. And my answer ends up being 25 moles. And there you have it, the ideal gas law and the combined gas.